Ladies and gentlemen, future production and logistics will be based on biointelligent networks and ecosystems. After the development of individual systems and autonomous machines within the context of the Fourth Industrial Revolution, the central research question of future production will concern the creation of a virtualized ecosystem in which humans and machines can interact in a social way. It's about developing a social networked industry, the complexity of which will also require disruptive technical change. As with the development of individual autonomous systems, there are good reasons to think about natural analog processes and natural habitats as a model for such a bio-intelligent environment. You will ask why? Well, because the only thing that survived in the last 3 billion years was evolution itself. The probability that something like a human being stands at the end of the evolution is so incredibly low that we should take a look at it. Even the slightest deviation from natural constants would give a completely different direction to evolution and in most cases prevented an evolutionary development as we know it today. The deeper we penetrate into the material world and its decryption, the more visible it becomes that it requires exactly these one biosphere and nature to produce humans who are able to think about themselves. If we talk about the development of biointelligent value-added services and systems and their technical manifestation, we should therefore think about what an adequate environment, let's call it the technosphere, looks like, in which real artificial intelligence can emerge. I don't want to focus on a single individuals, on neural networks, the metabolism or the sensory systems, but on the spheres as a whole. Let's take a look at the insights that are needed to be learned from the point of view of production and logistics. And let's see what kind of natural constants are required for spheres of artificial intelligence. Let's start with the easiest one, the single-cell organism or protozoan, similar to those shown in this picture. This is how a technical protozoan, like the so-called low-cost checker, looks like. Enough energy for its lifetime on board, in this case up to 10 years. Alternatively, the power consumption is so low that the cell can supply itself via a solar cell or via an air interface. The cell can be networked and roughly located via 5G-compatible narrowband IoT. For close-range communication and localization via Bluetooth LE is also integrated. The cell perceives its environment via acceleration, temperature, humidity and position sensors, an important factor because real artificial intelligence will not arise in a vacuum, but it requires communication and interaction with its environment. The computing power of the cell is sufficient to carry out simple AI algorithms, for example, for sensor data analysis. By the way, before I came to Fraunhofer, I was an entrepreneur. In the early 90s, I built the first warehouse, the first large warehouse, and at that time, we used a 90 MHz Pentium server, single-core CPU with 128 MB RAM. Of course, at that time, we connected 70 clients to the server, and our protozoan is not able to connect to 70 clients in a proper way. But integrated is a CPU with 1.2 GHz and 2 cores. And this CPU, integrated in our protozoan, costs just 75 cents. Incredible, isn't it? Biological systems reproduce themselves exponentially if the proper environmental parameters are given. The technical environmental conditions are undoubtedly present, and the exponential growth, in the sense of undistributed reproduction, will occur if the economic conditions are given. Beside the technology with a target price of €10 and a flat rate of €1 per year with 500 megabyte flat rate for 10 years, all conditions for an exponential growth should be given. And the development is unstoppable according to our experience, because technical possibilities have always been used in human history when their time had come. And at the moment, we hold more technical possibilities in our hand than we can make good use of. The consequence will be a technology explosion, similar to the Cambrian explosion of species 540 million years ago. Now, logistics will play a decisive role here, because logistics is responsible for the organization and design of all kinds of physical movement. This concerns the movement of all parts, producing both a car or goods of our daily life. So if we stick on the example of our logistics protozoan, it will be its job to move things in a reasonable way. In the simplest case, we are talking about a container or a pallet which moves on a conveyor system, as it happens every day in factory buildings all over the world. The organization and control of such a system is always done centrally by a production planning system of something like that. Even if the control modules are decentralized, the implemented algorithms are always heuristics accessing a central database that is updated as far as possible in real time. In this context, the analogon of a central brain and related sensory systems, nerves and blood vessels is often used for the design and architecture of material flow systems. The image of an organism with its central brain is a typical human view, but completely unsuitable. In reality, we are mainly dealing with loosely coupled systems. In nature, we would speak of multiple individual organisms. This is a picture we should have in mind. Nature came never up with the idea of introducing a centralized production planning system. Now, applied to a common material flow system, this does not only mean modularization, decentralization and self-control, as we discussed in the context of Internet of Things and Industrial Revolution some years ago. In a cellular transport system, each logistical protozoan has its entire construction plan, in our case, the complete material flow diagram of the entire system. This is a decisive difference to classical designs in the sense of the Internet of Things. In a cellular transport system, each individual protozoan or cell has the entire genome. All cells are the same. Each protozoan is basically capable of controlling every single part of the entire system. Each individual protozoan is also able to adapt and learn and can pass on the lessons learned to the next software generation. Cells can duplicate themselves and passing on their information to future generation. And last not least, each cell has its own antivirus program. This security by design is one of the most important points in this highly scalable system architecture and is today in many cases, let me say, criminally neglected. A very, very decisive point. Now, the standardization in the design is also the basis for the so-called cellular transport systems or cellular swarm that you see here at work. It works like an ant swarm. The shelf corresponds to the nest and the workstations to the feeding grounds. Here the same basic principles are applied as for our logistic protozoan. All vehicles are basically the same. In principle, any vehicle can take on any task. For this purpose, It has two chassis so that the multi-shuttles, the cells, can operate in a shelf but also on the floor. All vehicles share a common map. As in nature, there is no central control, absolutely no central control. The model of self-organization is a swarm of ants. The model for the organization of the material flow is the ant trail. In general, transport systems based on more or less autonomous vehicles are a major trend not only in logistics and production, and of course also an exponentially growing market. The exponential development of technology, especially in the field of sensors and algorithms, has led to a veritable hype about a new vehicle class. This picture shows a completely autonomous vehicle which we developed some months ago for BMW. Nowadays, BMW produces these vehicles in large numbers by themselves. Remarkable, the first autonomous BMW. Now, if we add the third dimension, we get the drone swarm. The basic principles are again the same. Each drone is autonomous, all drones have the same genome, all drones react in the same way, and so on. We use this swarm to develop algorithms for autonomous driving and flying. For this purpose, a 600 square meter experimental hall is equipped with an optical localization system based on 38 high-resolution cameras. That gives us the position of all the vehicles, containers and drones with accuracy of 0.2 millimeters in all three dimensions in less than 5 milliseconds. I'm also impressed about these numbers, and I think this is also real high technology. Moreover, a biointelligent transformation will consequently affect the interface to humans. Here worlds meet. People communicate with gestures, images and languages. The net information flow of the communication never exceeds the limit of just 300 bits per second. But the effort for the digitized interpretation of human language and gestures is considerable. It seems to make sense to provide both sides with suitable interfaces like 3D cameras, the 3D systems and artificial intelligence combined with attributed-based recognition systems. This video in behind shows the vectorical motion capturing basis of any kind of analysis or algorithms for the motion capturing system and the motion attributed calculation. There's another example, and it shows how a human-machine interface may look like. In this case, the interface is realized with motion sensors that human wears as a wristband. With those and combined with a suitable AI algorithm, the vehicle can recognize gestures and calculate the distance to human in a relatively simple form. While the vehicle itself reveals with an animated face what it has in mind or whether it has understood the person in front of it. If Emily looks sad, the vehicle was named Emily by her inventor Jan Joost. If Emily looks sad, she did not understand what she was told. The face also indicates where she wants to go to, or if there are any problems, and so on. The interpretation of natural language is much more complex. Think about indirect question jeopardy, for example. But it has reached the mass market with Alexa, Amazon Echo and OK Google by now. I'm convinced in a few months it will be quite normal to talk to a shelf. And it will take just a few years and the shelf will notice whether I understood what the shelf intended to say via plethysmographic blood pressure measurement, for example, with an infrared camera system. Also, complete virtualization in the form of three-dimensional real-time simulation of physical systems or simulation-supported monitoring of complex systems has reached the shop floor. We are on the verge of no longer being able to distinguish whether we communicate with a human being or with a machine. We can no longer distinguish whether the virtual reality around us is a representation of a real world or an artificial world, artificially created for my individual requirements. This video shows a real-time simulation and animation. This is not an offline rendered cartoon. It's a real-time rendering using the ultimate game development platform Unity, deployed on a conventional graphics CPU. Unbelievable. Since 1950, the Turing test has been considered as a kind of holy grail in the development of artificial intelligence. Its point is that in communication between a human being and a computer, it's no longer possible to distinguish who is the human being and which is the computer. But that's not the question anymore. Even the computing power of our logistics protozoan is sufficient to run a simple AI algorithm. The big question is, how does an environment look like in which real artificial intelligence can grow up and interact with humans reasonably? The biospheres of artificial intelligence are of virtual nature. Their genomes are cast into program codes. If they are intended to reproduce themselves and inherit what they had learned, virtual rooms must be made available that provide the corresponding communication and computer power. Digital biospheres are habitats for humans and machines. The organization and cooperation will be similar to social networks in the internet. They are the only form of interaction and self-organization of millions of individuals we know. In a so-called social networked industry, human and machines will work together in partnership. At the same time, biointelligent systems will be developed which will only be successful if they enable both human and machines to work together in a social way. Thank you very much for your attention. All the best from Dortmund.